Chapter 13, a new chapter, vector-valued functions and motion in space, in three-dimensional space. So our first section here, section 13.1, curves in space and their tangents. So some learning goals. You should be able to graph vector functions and identify vector functions from graphs. You should be able to understand notions of limit and continuity and differentiation for vector functions and be able to apply differentiation rules. So, big question here, I guess, is what is a vector-valued function? Vector function, vector. So let me write here. We'll use these two terms interchangeably. A vector function or a vector-valued function. And so it's a function that looks like this. So the output is going to be a vector, r vector here, r of t, is equal to, like let's say x of t, y of t, z of t, or using I hat, j hat, k hat notation as we frequently do in this class, x of t times I hat plus y of t times j hat plus z of t times k hat. And so the input here is t. We input in t, which is a parameter, which is, I guess I should emphasize this as a scalar. And also I should emphasize, not always, but frequently, we're going to think of t as time. So there's a decent reason to use the letter t here. Not always, but frequently we'll be thinking of t as representing time in some way. And then the output that we get from our vector function is a vector. So we're going to have this entire chapter on vector functions here. Actually, we've already seen vector functions. We've seen an example of vector functions already in this course last chapter. So let me just write down an example here. R of t is 1 plus 2t I hat plus 3 minus t j hat plus 4t k hat. When do we see, maybe not this exact one, but when do we see something like this? Well, this is a parametrization of a line. And so parametrizing a line is one example of a vector function. There's lots of other examples, and we'll do that, but we've already have talked about parametrizing lines. Let me make some other comments right now in this intro video. So something we should talk about are paths and curves. And so the idea here is that, okay, so this is just a straight line in moving in three-dimensional space. But we're definitely going to end up with more complicated figures or something like that. So we could have something, this looks vaguely like a saddle or a Pringles potato chip or something like this. We have a particle moving along this path here. And so the idea is that all of the points reached by r of t make up the path. Or the curve, I guess. So I guess let me some textbooks distinguish between path and curve. This textbook really allows you to use path and curve interchangeably. I guess that the idea here is that we have some curve in space. That's the set of all points that you would get to from R of t. And then if you're thinking about a particular, as soon as I put a little dot on here, I'm thinking about a particle moving through space here along the curve, then that's, so this is a particle moving along a curve, gives you a path. And we so frequently will be talking about particles moving along the curves that we'll be using path a lot. The distinction here is probably not the most important. Let me also, a couple more comments to make in this video. So we have vector functions, vector function would be R of t. So now that we're going to be calling this, I'm going to start using on occasion the term scalar function, which would be like f of t, which would be the usual function that you've been spending so much of your life studying here. F of t is equal to t squared plus t minus 1 or something like that. This is a scalar function because the output is a scalar. R of t is a vector function because the output is going to be a vector. If we were to, for example, R of 1, plug in 1 into here, you get 3i hat plus 2j hat plus 4k hat. The output of this is a vector. And then one more comment that whenever we think about new classes of functions, we should think about like domains and stuff like that. And so domains are usually, not always, but usually all values of t for which R of t is defined. So, for example, if we were to have R of t is equal to, let's say, t comma natural log of t comma e to the t. Well, natural log of t is only defined for strictly positive values of t, so the natural domain here would be t greater than 0. Okay, so this is an introduction to vector functions and vector valued functions. We'll use those terms interchangeably. Next, coming up next, we'll be drawing some pictures. What do these look like?